Alors, bon matin et bienvenue à cette session sur l'or et roches sédimentaires, une combinaison gagnante partout sur la planète. Donc, dans cette section, on va étudier ou voir des exemples et essayer de comprendre la relation entre l'or et les roches sédimentaires qui est extrêmement importante parce que si on regarde autant dans les roches archéennes que dans les roches protérozoïques que paléozoïques et de l'Archéen à l'Éocène, on retrouve les plus grandes concentrations d'or, ou presque, dans des roches sédimentaires. Donc, c'est une association qui est souvent peut-être moins mise en évidence dans notre contexte de ceinture de roches vertes de l'Abitibi, mais c'en est une qui demeure extrêmement importante dans ce contexte-là, comme on l'a vu récemment, et aussi dans les ceintures paléozoïques, comme les Appalaches, comme on peut retrouver dans le sud du Québec. Donc, pour débuter la session, on a un conférencier émérite, le professeur Ross Large, qui est professeur de géologie économique et directeur du centre CODES, un centre d'excellence en Australie, à Hobart, Tasmanie. Ross a reçu son baccalauréat spécialisé de l'Université de Tasmanie en 1969 et un doctorat de l'Université de Nouvelle-Angleterre en 1973, avant de faire un stage postdoctoral à l'Université de Toronto. Au cours des 10 dernières années, il a travaillé dans divers projets d'exploration dans les territoires du Nord en Australie, au Queensland et en Tasmanie. Et en 1984, il s'est joint à l'Université de Tasmanie et 5 ans plus tard, il a fondé l'organisme CODES, qui est un des plus importants centres mondiaux de recherche sur les gîtes minéraux et qui est financé conjointement par l'Université de Tasmanie, l'industrie minière et le gouvernement fédéral d'Australie. Sous sa direction, CODES est maintenant reconnu comme l'un des meilleurs centres de recherche sur les gîtes minéraux du monde. Il est composé de plus de 40 scientifiques, 80 étudiants gradués, et un budget d'exploitation d'environ 10 millions de dollars par année. Sa recherche a impliqué une étroite collaboration avec l'industrie minière mondiale afin de déterminer les facteurs géologiques et géochimiques qui contrôlent la genèse et l'exploration des gisements minéraux. Donc, j'inviterai maintenant Ross Large à me présenter sa conférence. Ross.
Bonjour, and thanks very much, George, for those very kind words. I'm afraid that I will be speaking in my native tongue, knowing very little or zero French. So I hope you'll bear with me. I have quite a broad accent, so I will not speak too fast so that you may be able to understand me. It's a great pleasure to be here, and thank you very much to the organising committee for inviting me to this session. It looks as though it'll be a very exciting session with some new ideas being generated now in gold ore genesis. I think it's an exciting time to revisit some of the models of the past and think about directions for the future. So thank you very much for this opportunity. I want to talk about sediment-hosted gold deposits. These are strata-bound and cross-cutting styles of gold mineralisation. They're disseminated arsenic-bearing pyrite, usually. Pyrite contents varying from about 1% to 5%, usually in that range. The host rocks are dominantly black shales, siltstone sands and carbonate facies. They're typical marginal marine continental margin type sedimentary basins that these form in. And previously these ores have been termed either orogenic gold deposits or turbidite hosted or Carlin types of mineralisation. So rather than using the conventional terminology of orogenic and Carlin type, I'd rather use a terminology based on the host rocks and therefore classify all these as sediment hosted gold deposits compared to the well-known greenstone hosted gold deposits. Some of the deposits of this style and the bigger ones outlined in yellow there, ranging in age of the host rocks or the sedimentary basins that they occur in, from the Cretaceous through to the Paleo-Proterozoic. You can see there the Natalka deposit in Russia, a large Permian deposit, the Carlin deposits, Muruntau in Central Asia, Bendigo, the Getchell district, another Carlin system, Suko log in Russia in the Siberian terrain, Telfer in Australia, Olympiada again in Russia, Shanti in West Africa, and Homestake, of course, in the USA, are all examples of significant tonnages of these deposits. In fact, when you plot up the sediment-hosted gold deposits, and obviously the greatest of these is the Witwatersrand system, but I'm not talking about that today. I'm talking about the black shale-hosted systems. But when you plot up the sediment-hosted gold compared to greenstone-hosted gold, the sediment-hosted dominate the sequence in terms of total tonnage of gold. So we're talking about deposits like Suko Log in Russia that we've done a fair amount of research on, the Karlin district, and those that are in the turbidite sequences such as Bendigo and Maguma here in Canada. Now these deposits occur, Suko Log for instance, as an elongate body that cuts across the stratigraphy within a sequence of shales and siltstones in this overturned anticlinal structure with carbonates above. A typical Karlin long section here showing that there's a lot of structural control on the mineralisation, shown in yellow here in all cases, but there's also a broad stratigraphic control in that the main deposits are occurring within the Popovich Formation and going down into the Roberts Mountains Formation, as you can see here, largely within carbonaceous siltstones and mudstones. Here in the Bendigo district we have less of the carbonaceous material as we do at Maguma, and the black shales here are the tops of turbidite cycles with sandstones dominating, but with quartz reef systems occurring usually at the contacts between the black shales and sandstones. So the overriding similarity of these styles of deposits are carbonaceous siltstones, mudstones. So I like to think of the spectrum of sediment-hosted deposits of a spectrum that ranges in metamorphic grade from those that are sub-green schist facies, such as Karlin-type deposits, to those that are moderate metamorphic grade, lower to upper green schist, and most orogenic deposits fall in that metamorphic grade range, to those that are high metamorphic grade amphibolite to granulite facies, of which there are much lesser numbers in that category. If we look at the mineralogy broadly of that spectrum of deposits, the low metamorphic grade deposits generally have refractory gold locked up in pyrite or in arsenopyrite. The moderate metamorphic grade deposits are commonly a mixture of free gold and refractory gold, with pyrite and pyrrhotite becoming more dominant, and the high metamorphic grade amphibolite to granulite are nearly always free gold, total free gold with other minerals such as lollingite, arsenopyrite, and pyrrhotite dominates over pyrite. Although you might get a second generation of pyrite coming into those high metamorphic grade deposits, which is replacing earlier pyrrhotite. So in this talk, I want to challenge three fairly common beliefs related to orogenic and Karlin-type deposits. Firstly, the gold is coming from some deep source or from crustal granites, and I'd suggest that the gold is already present in the sedimentary basin. You don't have to introduce it from far away. Secondly, organic rich sediments are good trap rocks for gold. Yes, I'd agree with that, but organic rich sediments are also ideal source rocks for gold and arsenic and a whole lot of other trace elements as shown there. And thirdly, the general perception that gold is introduced late is syntectonic or post-tectonic. We would challenge to say that gold is introduced early, it's already in the basin, it's pre-tectonic, but it's moved around during tectonism to then appear to be late tectonic, but it's only because it's moved into those late structures during basin evolution that happens. So let's have a look at some of the current models. The source of gold fluids, this is a model of Kerrick and others, suggesting that the gold is coming from fluids that are generated at considerable depth down here beyond 20 kilometres in amphibolite facies and moving up to deposit in shallower parts of the crust between 10 and 15 kilometres depth. Or another model here showing fluids coming off very deep igneous intrusions or coming off the slab, the subducting slab here at considerable depth, 10 to 20 kilometres depth. Another model for kaolin-type deposits from Gene Klein, again suggesting that very deep magmas are important in the genesis of these deposits in releasing gold and fluids of various compositions that are being also added to by crustal fluids to eventually form the deposits at very shallow depth within the crust. Another genetic model for kaolin-type deposits and some of these distal types of mineralisation, showing again the concept of a very deep magma chamber that's bringing in the gold. Why do we need a new model? Well, we're involved in an AMIRA project, the Australian Mineral Industry Research Association, for now 6 years, and we've published a number of papers out of that. But it was also stimulated by previous ideas that are well entrenched in the literature, such as that terrific book of The Green Bible of Boyle's that came out in 1979, which is always a great reference when you want to look up the past ideas on gold deposits. Buryak, a great Russian geologist whose work was fundamental in the discovery of the Suko log deposit. Krybeck, Paul Emsbo and his ideas that were generated in 2000 and before on the Carlin district, and Ian Pitcairn's work in the New Zealand deposits. They've all been instrumental in developing our thinking on these types of deposits. There's two key elements we would suggest that I want to get across to you today. The gold's not sourced from great depth, but it's already in the host sediments that either are lateral to the ore deposits or below the ore deposits. And these deposits are really arsenic deposits with accessory gold. And when you're considering the source of the gold, you cannot not consider the source of the arsenic. You can't separate them and say, oh, the gold's coming from here and the arsenic's coming from there, and then we're all happy they're going to get together and form an ore deposit. Now, let's be realistic. They're the two main components in the ore body, and they're probably coming from the same place, coming from the same fluid. So the summary of the model that I'll be giving to you is that gold, along with a series of other trace elements that are fairly typical, arsenic, nickel, lead, zinc, vanadium, molybdenum, selenium, copper, uranium, sometimes the platinum group elements, are initially concentrated in organic rich sediments by reduction and absorption from seawater. That early diagenetic pyrite becomes enriched in arsenic and gold and other trace elements to levels of 0.1 to 10 ppm, and that thick accumulations of gold-bearing black shales may develop in this way in continental margin sedimentary basins. And metamorphism and deformation, and sometimes igneous intrusion, releases the gold trapped in the organic matter in the diagenetic pyrite, resulting in upgrading and concentrating the released gold into the favourable structural trap sites. So let's have a look at, pardon me, I might get a bit of water, George, thanks a lot. I'm a bit croaky today.
Long trip.
Yes, we spent my wife insisted that, seeing as we're coming this far around the world to come to this conference, that we had to spend a week in New York before we got here. So we've had a great week in New York. Thank you. Right, so the first process is how do we get the gold into these marginal sedimentary basins? Well, we would say it's basically just gold that's being eroded from the hinterland, comes down the river systems as probably colloidal gold and micro nugget gold in the river systems. It comes into the continental margin basins, and particularly during periods of anoxia, where you've had more reduced environment in these basins, and you've had a transition from an oxic to an anoxic in these basins, and you've had a transition from an oxic to an anoxic environment, then these clays and humic material that has the gold absorbed on it, moves in with a whole lot of trace elements also attached. These trace elements get reduced, as does the gold, to a lower valence state, and then eventually gets complexed in to form humic organometallic complexes. And these are pretty well understood now in the literature, these complexes, and they trap the metals in the organics in these black shale horizons. And the carbonaceous sediments can be enriched from anything from about 4 parts per billion up to 100 parts per billion by this process. It's rare to get enrichments above 1 ppm. But this is an early concentrating process that we're looking at here. The organic fixation is thought to relate to certain organic compounds. The gold 3 is reduced to gold 0, which then complexes with the organics, particularly on the sulfur and nitrogen sites of organics, and amino acid impurities are thought to be pretty important in these organic complexes. So it's only certain types of organics which will effectively trap the gold in these organic rich sediments. So the way we envisage this process, and I think this has come out of work on the Carlin system mainly, because there it's a very low metamorphic grade and you can still see the organic matter in the bedding, and you can see organic matter that cuts across in veins, and we can analyse these layers of organic matter and see the trace elements in them. During diagenesis, a lot of the organic matter in these sediments actually oxidises and the gold is released, and that gold moves into diagenetic pyrite that is growing at the same time. So the oxidation of organic matter is at the same time in parallel with the formation of diagenetic pyrite by the reduction of sulphate in seawater to form H2S and pyrite. And that pyrite that grows then in these muds has all the elements in it that came off the organic matter. So that's the idea, that we move the gold from the organic matter into the pyrite. Not all of it, but and this depends on degree of diagenesis and metamorphic grade. So we're starting off here as the pyrite grows now during early diagenesis. It usually grows as these little clusters of microcrystals we call pyrite 1, and these have elements such as arsenic, gold, nickel, cobalt, silver, lead, copper, zinc, tellurium, selenium within those pyrite grains as they grow. During later diagenesis, they usually get overgrown by a second generation of pyrite, which has less trace elements in it. It still has a group of trace elements, as you can see there, but this is where the gold was enriched in this core usually. And we start to see very minor inclusions of chalcopyrite and sphalerite and galena at this stage, also during light diagenesis. Then as we go to early metamorphism, there's usually an overgrowth now of later generation of metamorphic pyrite, and this is more euhedral in nature, pyrite 3 here. This is usually cleaner with less trace elements in it, no gold in it, but it still has little blebs of chalcopyrite, sphalerite, galena, and also pyrrhotite start growing in that. Now, at higher levels of metamorphism, and this is getting into mid-green schist facies, these pyrites get replaced by pyrrhotite. And that's when you release most of the gold from this early diagenetic pyrite. Because pyrrhotite cannot contain gold in its structure. It can't contain arsenic either. And therefore the arsenic and the gold are released to a metamorphic fluid, and we get left with pyrrhotite that has a bit of nickel, cobalt, selenium, etc. And it usually has little grains of chalcopyrite and sphalerite and galena around it, telling you that it started off as a metal-rich pyrite, and those metals get released to just form little grains around the pyrrhotite. So the process, we think, if we apply that to Suco log without going through all the geological information for this talk, is that we had a continental margin basin in which we deposited these very organic rich sediments, the Comalco Formation as it's called, that was anomalous in gold, and during metamorphism folding and thrusting. The pyrite in the deeper part of the pile was converted to pyrrhotite. It released its gold and arsenic, and that moved up along anticlinal axes to form the gold deposit in one of these carbonate seal sites in an overturned anticlinal structure. And if we look at the Google map of the region where Suco log is, you can see on that map a broad anticlinal structure here. And if you detail that, you can see this is the Kamoko Formation, the organic rich shales. This is where the gold deposit occurs here, the Suco log deposit. These are the drainage systems that have alluvial gold and have been mined for alluvial gold. And all you need to do is actually concentrate the gold that is anomalous in the sediments from this area, about 15 cubic kilometres at 30 ppb gold, and drive it up into this nose, and you've got the Suco log deposit, which is a very large disseminated pyrite gold deposit. So as I said, these models aren't new. If you read Boyle's work, he discusses how gold can be enriched in organic rich sediments, as does Buryak and Krybeck. They've come up with leaching models of these types in the past. However, these ideas have really been ignored over the last 25 to 30 years in favour of a deep source for gold. And that's been driven largely by the fact that we see major gold deposits lined along very major structures. And the thinking there is that those major structures have been the source or the channel way for fluids moving up to the surface. That's not necessarily the case. The major structures may just be breaks in the structural framework that have been boundaries for fluid flow, fluid moving up along those boundaries to form deposits. So these are the sorts of carbonaceous source rocks we're interested in: Suco log, the Carlin Trend, Bendigo. In the Carlin deposits, you can see during early metamorphism that they're so organic rich that the organics are being released to form these pyrobitumen calcite veinlets that cut across the stratigraphy here. But we've still got quite a bit of organic matter in the layering of these rocks. Now, if we look at the literature on the gold content of potential source rocks in gold districts, whether they be in greenstone districts or in sedimentary basins, you find from the literature, and this is just going into the literature of Crockett and Boyle and recent work by the Russians, all comes up with the same numbers basically, that the most gold is found in strongly anomalous carbonaceous shales, up to about 50 ppb gold. Then normal carbonaceous shales are usually between 6 and 10 ppb, followed by tholeiitic basalts at about 6, granites, etc., normal shales about 2, and then you go right down, average mantle about 1 ppb gold. So obviously carbonaceous shales are a great candidate. And if we look at arsenic, the other most important element that you cannot forget about, then that is also enriched in strongly carbonaceous shales, followed by carbonaceous shales, none in basalts or granites to speak of, a little bit in shales. So it's very difficult to argue that your gold is coming out of the mafic volcanics. You can argue that, but you have to forget about the arsenic if you do that. But these are arsenic and gold deposits, and I'll introduce tellurium a bit later, and we've got to worry about where the tellurium comes from too. So carbonaceous shales, I'd maintain, contain 3 to 30 times the average crustal gold and from 15 to 100 times the average crustal arsenic, and no other rocks have these characteristics. Now, where is the gold in these shales? There's only a small amount, but where is it? And the Russians have looked into this. They'd suggest, Krasov's published that gold in black shales is absorbed onto organic matter, around 50 to 60%. There's invisible gold locked in the structure of pyrite, I've talked about, 30 to 40%, and they even found gold absorbed onto detrital K particles, 10 to 15%. This is an example of a shale from the Roberts Mountains Formation in the Carlin district, so this is the lower carbonaceous sequence there. And these are laser ablation analyses. Oop, I went forward, I should have gone back. How do I go back? The red one. Thank you. Pyrobitumen here, you can see was analysed to have about 5 ppm gold and a lot of arsenic and vanadium. Vanadium is a real good indicator of organics, silver, etc. And you look at the pyrite's got some gold in, much less than the organics, and other elements are still anomalous, as you can see. Molybdenum, characteristic of diagenetic pyrite, very anomalous there, as is the nickel. So we've still got a fair bit of the gold in the organics here. We haven't moved all of it into the pyrite, but generally with increasing metamorphic grade, that'll eventually move into the pyrite. Here's a laser ablation trace across just a normal black shale, again from the Carlin district down in the Roberts Mountains formation, and you can see that this is the trace of gold going across this shale. This is only about 1 millimetre of shale that we're analysing, but you can see it's averaging about 78 ppb gold, and there's little spikes, and every time there's a little spike in gold, you can see there's a spike in arsenic and a spike in iron, indicating you're going across a very small pyrite grain that has higher levels of gold. But even the background in the carbonaceous sediment is a high background for gold. The best method of showing this association of gold with organic matter is to just do whole rock analyses of the shales and plot gold against other trace elements that we know are concentrated by organics, and vanadium is the best one. Gold and vanadium. If gold and vanadium correlate, you know you've got an organic gold association. Gold and arsenic, you can see here, gold and nickel are correlating well, and gold and zinc are correlating well. These are the group of elements we call the VAMS-NAS elements. V for vanadium, A for arsenic, M for molybdenum, selenium, nickel, silver, zinc. That simple suite of elements are the ones you're looking for this organic concentration process, and they're known as redox sensitive elements. They're very sensitive to changes in redox conditions that'll cause a change in valence state and organic complexation. And in addition to those elements, obviously copper is another one. We couldn't work out where to put C in that, so we left it out. But otherwise, you know, they're the elements you're looking at. This is the sort of pyrite you're looking for. You're looking for early diagenetic pyrite, such as we see in Suco log in the black shales there, really fine crystals of pyrite. Sometimes they're little networks that look as though they probably started off as marcasite that are partly recrystallised to pyrite, or in the Carlin district, they're generally these little elongate football shapes that have very small microcrystals of pyrite in them, and they're the ones that have the best levels of gold in them usually. We've now developed a database of black shales from around the world. We're collecting shales from Archean through to the recent to look at the chemistry of the shale and the pyrite to try and understand how they've varied through time. And when you plot up all the data we've now got on diagenetic pyrite from black shales around the world and plot gold against silver, then this is the cluster of data you get. And we're not going out and just picking black shales from gold districts. We're picking black shales from anywhere. In fact, if they're not in a gold district, that's even better for us because we want the background. But this group here includes all the background shales that have got nothing to do with gold deposits, plus shales that are around gold deposits, and that's the pattern you get. So there's obviously a very good gold to silver relationship for the dominant population here. It's nearly always has silver greater than gold, and that's a characteristic of diagenetic pyrite. When you get across that line of silver equals gold, you're normally getting into the hydrothermal pyrite field. So these few analyses here may represent some samples that have got hydrothermal pyrite in them. And that works for lots of districts. It works for the Carlin district. It works for orogenic gold deposits. It's probably the most simple chemical parameter to do with diagenetic pyrite. And that's a line we would put on that diagram to say if you've got more than 0.25 ppm gold in pyrite, then you're probably in a gold district. they're the sort of numbers you need to be looking at, that upper part of this trend, to be generating gold deposits. Here's the gold tellurium plot. Here's the gold tellurium plot. Even better. Who would have thought that by analysing diagenetic pyrite, you get a really good relationship between gold and tellurium? Even down at this end here, where we've got very little gold and tellurium, they're still showing a correlation that goes right through the data set. So we'd put our line there again. You're looking at, just going back there, you're looking at gold above 0.25 and tellurium above about 1 ppm in pyrite. Remember, these analyses of pyrite, they're not analyses of whole rock. You've got trouble using this for whole rock because we're looking at pyrite because it's concentrating these elements, and you can get much better analyses by analysing the pyrite. If you analyse the whole rock, you need a really good analytical method that gets you to much lower detection limits. This is gold mercury, and again, you can see a very good correlation between gold and mercury in diagenetic pyrite. Now, we've used a laser ablation mapping system to map the hydrothermal history, or the diagenetic to hydrothermal history of pyrite. We look at the textures of the pyrite in particular. We etch the pyrite with acid, and that brings out a lot of texture that you can't see just in the normal reflecting light microscope. And then we analyse the pyrites for a whole lot of trace elements and look at the metal concentrations in the pyrite. So the first part of the process is doing the petrography, looking at the different types of pyrite, documenting them. These are all diagenetic types of pyrite. We're coming here to diagenetic pyrites being overgrown by metamorphic pyrites, these early diagenetic pyrites that have tails on them that are in the pressure shadows developed during metamorphism. But the important thing here is that metamorphism does not destroy the early textures in pyrite until you get up to mid-green schist, upper green schist facies. We can still see these early diagenetic textures even though we're growing a later metamorphic pyrite over the top of them. So this pyrite petrography is extremely useful. Here we can see more metamorphic type textures here, more euhedral nature to them. This Christmas tree type growth is fairly common in pyrites. And here's a pyrite where it's overgrown the metamorphic fabric. It's got an early diagenetic core, and then it's got overgrowths which actually have retained the metamorphic fabric. So this is a late metamorphic pyrite in this case here. These are some other pyrites that are growing in quartz veins from the Bendigo district. So this mapping technique we use is to laser across the sample to build up a picture. It's like doing an aeromagnetic survey, but it's doing it over a pyrite grain at a micron scale, basically. And all the fluid, all the gas that comes off this ablation goes into the mass spectrometer and ends up giving us a picture of what the trace elements are in the pyrite. So this is a nodular type of diagenetic pyrite. The gold picture shown here shows you the gold's concentrated in the middle and lesser gold, but there's still gold at the outside. These are counts per second. They don't relate. They're not parts per million, but this would be about a ppm of gold in the middle and about 0.2 at the outside. You can see arsenic also concentrated towards the centre there, silver, etc. You've got a high silver to gold ratio, so you know that's a diagenetic pyrite, and you can see other trace elements. A little bit of moly right in the core. That's typical of the first growth related to organic matter. Nearly always has an enrichment of moly associated with it, and you can see vanadium also within these pyrites. Here's another really nice example of an early diagenetic pyrite overgrown by a metamorphic pyrite, where you can see that the gold in this is all in the core, right in there. There's an arsenic envelope around it, which is this growth here. You've got a bit of arsenic just surrounding the gold and then arsenic diminishing out towards the edge. You've got silver in the core, high silver to gold ratio, moly in the core, tellurium in the core, etc. And you can see a build-up of cobalt and nickel, which is common in the metamorphic stage of the pyrite growth. So that's the sort of pyrite you're looking for, which tells you that these shales were originally concentrated in gold. Here's a much more complex pyrite now from Bendigo, where you get an early growth of diagenetic pyrite, this sausage, which is overgrown by another late diagenetic pyrite, which is fairly clear, which is overgrown by a metamorphic pyrite, which has encapsulated the metamorphic fabric in it. So that's a very late metamorphic pyrite growth. And when you map that, you get a beautiful history of trace elements. And these are trace elements in the fluid that was moving through this siltstone to form the gold deposit that isn't far away. This was about 50 metres from a gold reef in the Bendigo district. And you can see gold, for instance, is concentrated in that early diagenetic pyrite. There's not much gold in the second generation of pyrite. It builds up to the edge of the final metamorphic pyrite, which also shows you this abundance of arsenic at the final stages of growth. And these are details then of that pyrite grain, which we can enhance using same sort of software as you do for geophysical data. These are spot analyses now showing you how much gold is in the core, about 0.7 ppm, about 2 to 6 ppm gold in the rim in that grain. So this is recording two gold events, an early gold event in the sediments and then a very late gold event during late metamorphism, and that's the event that moved the gold into the reefs to form the Bendigo reefs. So that's the model again, starting off early diagenetic pyrite, overgrowing it then late diagenetic metamorphic with a final rim of gold indicating the final pulse of gold in that system. And when you actually plot gold against arsenic for all those spots we put into those pyrites, this is the early event here, the stage 1 in the sediments, and then stage 2 that forms the ore bodies is this event here that's heading up towards high gold, high arsenic end of the spectrum. At Bendigo, we also found that as you get closer to the gold reefs there, within the sediments now, the rim of gold on the pyrite got thicker. So here you can see a pyrite with quite a thick gold rim developed on it. Thinner here, non-existent out here. So this is pyrite's going away from the gold reef. Same story here, very thick gold rim, getting thinner and then disappearing so that there's only gold in the centre of the pyrites in that particular case. Now I want to emphasise the relationship between arsenic and gold in these sediments, and this is from studies that Steve Kessler and his colleagues have been doing for some time at Michigan. Reich published a really nice paper with Kessler on this in 2005 and showed the relationship between arsenic and gold in pyrites and shales. And this is data of theirs, the plotting gold against arsenic ppm in pyrite from the Carlin district, showing you that all the pyrite is plotting down here. That allowed them to define this line they call the gold saturation line, where gold will go into Arsenian pyrite up to that line. Anything above that line, you're looking at free gold. But we know there's virtually no free gold in the Carlin systems, and therefore everything is plotting below that particular line. And this is telling us that the more arsenic you've got in the fluid, the more gold you can put in the pyrite. And that's up here. This is where you want your pyrites to plot, up here when you're looking for a Carlin system, because that's going to be the high-grade part of the system. Let's have a look, for instance, of comparing whole rock chemistry to this plot. So average normal sediments are plotting down here at probably about 10 ppm arsenic and about 1 ppb gold. Average Carlin Basin sediments are plotting up here, further towards 100 ppm arsenic. That's probably a little high, it's probably down in here, and 0.1 ppm gold. This is the average Carlin ore, plotting up here, and then this is the pyrite in the ore, which goes right up here. So this is the sort of trend you want. This average normal sediments won't produce a gold deposit. You've got to go through too many orders of magnitude to get there. Here, we've got a chance of producing a gold deposit, as you can see. And it's really, although there's two processes here, and I keep emphasising this early process, stage 1. This does not produce ore, stage 1. It's just the pre-concentration process in the sediments to get your sediments up to a point where when the deformation or intrusion takes over, you can concentrate the gold up to form an ore deposit. So this is the sort of model we've developed, a sedimentary basin with a lower section that has black shales in it, and those black shales can continue right up through the basin. And you may form quartz reefs like we do in the Bendigo district, or these structurally controlled deposits in anticlinal positions such as Suco log, or associated with carbonate reef systems such as in the Carlin system, with fluids moving up, carrying gold and arsenic up into these systems. Now, down below, this is what I'd call the source area down here, and there's been some deep drill holes under Bendigo where we've had access to look at these source rocks. What you find is that the shales don't have pyrite in them anymore, they have pyrrhotite in them. And this is what it looks like under the microscope. There's a lot more fabric to the pyrrhotite because it's softer than pyrite, it's easily deformed, it's easily strung out, and so this is what it looks like. But this reaction of converting pyrite to pyrrhotite is the key reaction that's occurring in the source area. And the reason that it's a key reaction is pyrite, the early pyrite, contains gold and arsenic and tellurium dissolved in the structure of the pyrite. When it reacts with water and organic matter in these carbonaceous sediments, during metamorphism, it produces pyrrhotite and releases H2S and CO2, but pyrrhotite can't contain those elements, so they have to be released in that process. And this is an example of that process going on. We've got some early pyrite being replaced by pyrrhotite shown there. And when you analyse that with a laser, you analyse the pyrite here, and we found it had 0.4 ppm gold and 590 arsenic, 17 silver, 14 ppm tellurium, and then you analyse the pyrrhotite down here. It's got no gold, very little arsenic, less silver and very little tellurium. So that process is releasing those elements. And we've done hundreds of analyses of pyrite and pyrrhotite from Bendigo, and when you average them out for gold, the pyrite average is 0.3 ppm, and you can see the range and the outliers there. The pyrrhotite average is about 0.08 ppm, so that's the difference. That's the gold that's being released. Arsenic, we're going from about 150 ppm arsenic in pyrite down to about 2 ppm arsenic in pyrrhotite. You can write more sophisticated equations that put the gold and the arsenic into the pyrite. The same story. The gold's being released most likely as a bisulfide complex, the arsenic as an arsenate acid, and we're generating a lot of H2S, and that's important in the transport of the gold. If we look at a solubility pH log FO2 diagram, the fact that we're down here on the pyrite-pyrrhotite transition, we're very close to where you've got very high solubility of gold as the gold sulfide complex, and that allows the gold to be transported away from that source area in this H2S fluid to move up to be deposited to concentrate the gold deposit. Now, if you average all the analyses we've done on pyrite to pyrrhotite to pyrite, sorry, you can see which elements are being liberated by this reaction. So arsenic over 99%, copper, zinc, antimony, tellurium, gold, manganese, and the elements that aren't changing basically, like titanium, vanadium and these other elements. Some of them are staying in the structure of the pyrite and aren't being liberated, and so they end up staying in the pyrrhotite also. Now, this is a pretty common feature in deep systems. If you have a look at the literature, we've done some work ourselves. Certainly it was described originally by Buryak in Suco log, and we've followed up and confirmed his findings there. Ian Pitcairn demonstrated it as a viable process in the Targa district. We've worked at Kumtor and shown that you've got the same process going on there. Prashenko has published on this happening at Muruntau, the big black shale sequence below Muruntau. All the pyrite's gone to pyrrhotite there. Kalgoorlie, Tompkins has published recently on the importance of the black shales in the Kalgoorlie greenstone succession in the liberation of gold and sulphur. And Stedman, one of my PhD students, has demonstrated that's a viable process at Homestake. Also, in the Poor Man Formation, you've got a big black shale sequence that's overland by the banded iron formations, and you've got a potential of moving a lot of gold up into those banded iron formations. So that's the basic process we're looking at of liberating the gold from down here from the shales. So that's the basic process we're looking at of liberating the gold from down here from the shales and moving it up into the overlying sediments. Now, what about the tellurium? I mentioned it a few times, and you can see that there's this very good gold-tellurium relationship in the sedimentary pyrite, and there's no problem in that being liberated also at the time of the pyrite to pyrrhotite transition. If you've got enough tellurium there, it'll come off when this pyrite goes to pyrrhotite along with the gold and arsenic and sulphur. So we've really got the whole basket of elements that we're interested in. And if you look at the relationship between arsenic and tellurium, it's a very interesting relationship. If you look at a whole range of ore deposits, we've got a few plotted there and some that I can't give you the names of, but you can see that the Carlin system, very arsenic rich, refractory gold, very low levels of tellurium in the pyrite from there. So although there's scattered tellurium, there's really nothing of significance in those Carlin systems. Macrae's from New Zealand is down at that end of the spectrum also. Then you get a bunch of deposits that are both tellurium and arsenic bearing that are in the middle of the system, and then you get really tellurium rich deposits like Kumtor up here that have quite low levels of arsenic. So this is where your early diagenetic pyrite is a tellurium rich pyrite without much arsenic in it, whereas down here in the Carlin system we've got a very arsenic rich one with a little bit of tellurium. Now there's more to this tellurium story because, as you'd appreciate, some of the best parts of our ore deposits are the gold telluride parts, and so understanding when the tellurium is released and how it concentrates the gold I think is very important in this process. Right, so I'll finish up now, just talk a little bit about fluid flow. The sedimentary and structural architecture of these continental margin basins is the control on the fluid flow. And we need to look at all the components in these basins. The sandstones are probably the main aquifers for fluid flow and the contacts between sandstones and shales. The shales are the source rocks for the elements we're looking at, gold, sulphur, tellurium, arsenic, and the carbonates are probably acting as impermeable seals. So there's not much fluid going through those carbonates unless they're brecciated along their margins, but they will act as seals for fluid flow, and you may be able to produce mineralisation again up against the carbonates because of their impermeable character. But I'd also suggest that most of the regional fluid flow is along the strata, and it's very importantly controlled by folding and relating folding. Most models of gold deposits, you see the fluids moving across the strata, along structures that are cutting across. In sedimentary basins, fluids move along the strata dominantly, not across the strata, and I wouldn't see any reason why that isn't the case for these types of deposits either. So we're largely looking at fluid flow along the strata in these cases. Again, in the case of the Victorian deposits, we're looking at fluids coming from down here, moving up along the strata. They can be moving up at depth also, but coming up into these anticlinal positions again, forming these classic reef situations as in the Bendigo strata. And if you've got a very sandstone-dominated system as we do at Bendigo, then you're going to form a lot more quartz in your reefs. If you've got very little sandstone and it's a carbonate shale-dominated sequence, you're not going to form any quartz because you haven't got an abundance of silica. So in the Carlin systems, again, I'd suggest that most of your fluid flow is probably coming along the strata from deeper in the basins and moving up. And it's being abutted against this carbonate reef system that we've got along the Carlin district. So I'd see similarities between those three systems in that way. So in conclusion, carbonaceous black shales in sedimentary basins and in greenstone belts are a viable source for gold, arsenic, tellurium and sulphur. They're not in greenstones they wouldn't be the only source because in some greenstone belts they're not very voluminous, but they are an additional source. But in sedimentary basins I think they're by far the primary source. Gold and arsenic, tellurium and sulphur are originally concentrated in diagenetic pyrite in those shales, and the conversion of pyrite to pyrrhotite is the key factor that is liberating those metals. And tellurium-rich shales can produce gold telluride ore systems compared to arsenic-rich shales producing gold arsenic systems. And I'd also suggest that this process commences at low green schist facies, not at higher metamorphic grades. We've been able to demonstrate at Bendigo that in the middle green schist, the lower to middle, you're seeing that conversion of pyrite to pyrrhotite that is key to the formation of those deposits. Thanks very much.
Thank you, Ross. On a du temps pour quelques questions. Marc.
Hi. You didn't talk about the relationship with some intrusions. Sometimes you have environmental intrusion. So what do you think about these relationships?
I think that they can be very important in some systems. I think at Kumtor also, although there's no intrusions exposed, the sulphur isotope data there suggests that you're probably mixing a magmatic sulphur with a sedimentary sulphur. The intrusions I see as a heat source that is circulating fluid, probably meteoric fluids, that will promote the pyrite to pyrrhotite conversion within the sedimentary package. So I don't see the intrusions necessarily the source of the gold or the metals. It's again come back to the arsenic tellurium story. If you're getting the gold out of the intrusion, you know, why are you getting the arsenic out of the sediments? You might as well get both from the same place. So I think the intrusions are just a heat engine that is allowing fluid flow and promoting that pyrite to pyrrhotite conversion.
OK, une dernière question.
Ross, not all basins are equivalent. What makes a good arsenic gold-bearing basin?
Very good question. I agree totally. Not all are equivalent, and from our database now, we can show that there's some basins are totally barren of gold within the diagenetic pyrite. I think it must come back to the source area of, you know, where is the basin? What continental margin is it on? Was the hinterland a gold productive hinterland? You know, was it an old greenstone belt or arc sequence that was eroded and brought the gold into that basin? So I would basically be looking at the relationship between continental margin basins and their hinterland and what is the potential source.
OK. Thank you, Ross.
Thanks a lot.